welcome. Today's episode of Garage Science is about polymers. Bob and I were sitting around here the other day and we thought, well, what's another topic we can use in our garage? We thought, when we looked around, we just thought we're surrounded by polymers. Now, it could be something hard polymers like this coat hanger or these it's a case to put grills and stuff in, that kind of thing. Or it could be something as simple as a water bottle, you know, something like that. You can also look at this rope. That rope's a polymer. Polypropylene, that's a polymer. In our safety gloves that we've been using, you've probably been using too when you go outside or anything like that. Those are all polymers. I looked around the house and I saw polymers, Band-Aids. Bob and I use quite a number of Band-Aids, so we have a lot of Band-Aids around, and they're polymers. That's what makes them stick. We looked in the medicine cabinet. Here's skin moisturizer. Look at that. The reason it's so thick is one, it's cold up here and rainy, but we're gonna move on anyway. And that's a polymer. It keeps it like that. This is for burn relief. Yeah, we have that problem too. But anyway, look how thick that is, and that's all caused by a polymer. Food-wise, pudding. Pudding is made thick because of the polymers that are in there. Containers to keep our food in. Polymers. They're all polymers. Now, Bob and I have some favorite polymers. Our two favorite polymers, which gets us in trouble a lot of times, are balloons and rubber bands. Now, you would never use a rubber band for anything other than its intended purpose, and neither would Bob and I. Anyway, these polymers are a little different than these polymers. These are pretty solid, and these gel-like, but these have a very special property. And we're going to look at the chemistry of that very special property, and then come back and show you, because of that very special property, what you can do with these, which is pretty cool. All right, so let's take a look at the chemistry. Okay, chemistry. Now, normally, when you're messing around with a balloon, say like this balloon, and you do something like this, that's what happens. But what if you use the same kind of thing, but you weren't so dramatic with it? Okay? Then we would work on that elastomeric recoverability. Let's see if we can do that. We have a sewing needle here and another balloon. Now, according to what we've been told, spiders. How can spiders be out when it's this cold? They said if you take this and you insert it slowly, it'll go in, go through the balloon. I can't see where I'm at. And you can get it to come out the other end. And it doesn't pop. Ah! And why is that? Elastomeric recoverability. What's happening in there? Here, hold that, Bob. Don't be afraid. Just don't hurt yourself. Stay right there. Stay. What's happening there is the molecules are sort of like a spring. And they have the ability to expand and contract, okay? To extend, elongate. And that's what they mean by that elastomeric recoverability. They can move without breaking. And because they can do that, you can put the needle through like that. Isn't that amazing? I find that amazing. And believe it or not, that's the first time I did that. I was scared to death. And we did it anyway. It works really well. We'll celebrate by breaking it the old-fashioned way. All right. We'll see. Okay, Bob, let's go show them how to do the chemistry of this now. Look, I did it again. Isn't that awesome? Okay, so, sorry, we have to be serious now. We're talking about chemistry. Balloon polymers. You start with one single molecule and you have a monomer. If you use two of them, you get a bimer, and three is a trimer, like tricycle and tripod and things like that. Try again. Sorry. If you put a lot of them together, it's called many. So that's where the word poly comes from. Many. Okay? Many put together. And they're joined in this network. Here we got this network thing going here. Notice that they're random in their orientation. Random, like your thoughts, okay? Random. Okay, so there they are, all randomized in there. Now, we're talking about latex balloons, like the one I just did. Sorry. Now, natural rubber is a polymer isoprene, okay? Now, when it undergoes stress, like, say, being locked in a house for 40-some days, whatever, the chains undergo what's called bond rotation. That means they can extend and they can elongate. And that's what makes rubber bands so wonderful, okay? Because you can stretch them, and that's what makes them so good, okay? So much fun to be used for their intended purposes. The chains, these things, these random orientated chains, are in a network. It allows for what's called elastomeric recoverability. Now think about it. Elasto, like elastic band, meric from monomers, that kind of thing. Recoverability, which means they can go back to the shape they were. And that, okay, that's so the needle slides between the chains. See, you can see that. Slides right between them. Okay. And the chains stretch because of elastomeric recoverability. They slide around the needle. And that's what makes it so special. That's how it works. Okay. Have a new respect for balloons now. And polymers. And maybe even Bob. Okay, so we'll see you next time on Garage Science.